Broder. I will be presenting about ManyCore processors and practical applications for them. I have a history in software development, mostly in mobile. I've worked for several enterprise organizations, and doing mobile, especially iOS development, it's incredibly confining. So I definitely think there's a need to open up that ecosystem. I think that GNU Linux and other BSDs are a perfect opportunity to try to get some more exposure to the movement. In that spirit, I run a blog called the Open Source Game Development Pipeline. I use it as an avenue to educate people about free, libre, open source software and also hardware. And most importantly, I believe very strongly that the tools need to be free. I think that free software and hardware are the future. So what is a ManyCore system? Well, many cores, tens, hundreds, thousands, typically multi-threaded. They're used mostly by large corporations and government agencies, Lawrence Livermore, NREL, CERN, IBM. But instead of calling it supercomputing, we now call it high-performance computing, or HPC for short. Currently, there are very few consumer-facing chip offerings, and they also are, the ones that have existed are very expensive. Intel Knights Landing has a chip. It's roughly $2,000 United States dollars. It's 64 cores with 4 threads each at 1.2 gigahertz. But recently, they just pulled it off the market. So now there's a bit of a gap. I also put the link to the article in case people want to take a look at that. So the way we're currently using these systems, mostly for high-performance computing, there's also big data applications that people are running these clustered MapReduce operations, and then scientific institutions are using them for calculations and modeling. So sounds fun, right? But are there other real-life practical uses for ManyCore systems? So what I'm about to show you is a software renderer I wrote. I'm going to show you the single-threaded version because I just want to show a comparison for single-threaded performance, and then if we tap into multiple processors, how that scales. So as you can see, we're getting roughly between 400 and 500 frames per second. This is a software renderer. It has perspective texture mapping. This is a Collada model that I wrote a Collada loader for. So that's being loaded, and then for this model, it's being rotated on all 3 axes. As you can see from the frames per second here, once we have more pixels we need to fill inside of our frame buffer, we're getting roughly 250 to 260 frames per second. And there's also, I should also mention, so we also have some shading going on here. There's a light that's in the scene, but the shading algorithm is fairly basic. It's just using flat shading here. And then the reason we have this flat color here is I just created a single color to be a texture. So now let's look at it from when we use all of the cores. And as you can see, we're getting close to 900 frames per second. And then even when we have more pixels we need to fill, we're still getting about 500 to 600 frames per second. Let's get that screen there. So the software renderer, it's written in C. The type of rendering it uses what's called scanline rendering. There are different types of rendering architectures that exist. The reason I chose scanline is because It's fairly common. It's typically used for high-performance rendering, but it doesn't always guarantee the highest visual fidelity without using different types of shaders and post-processing effects. The render is also parallelized using OpenMP. And as you saw from the frames per second, when we've parallelized it, it's approximately 3 times improvement compared to the single-threaded version, and it scales with more cores. But on top of that, further optimizations are possible. When I wrote this, it was very much an academic thing for me, and with OpenMP, I've really only just grazed the surface. I could add reductions, which would give me more control over how the data is being parallelized, which would up the frames per second. And then on top of that, if I were to take this architecture further, I would make it tile-based, which would make it faster. So what are the advantages of software rendering? Well, as algorithms improve, you don't need to redesign an entire chip. You can just compile and run. So rapid prototyping. Then, of course, there are fewer levels of indirection required to draw graphics. So I don't have to go and write a whole driver stack or create an API to interface with it. And then there's no GPU dependency. So I'm not potentially interfacing with something that's proprietary or closed and going against the spirit of free software. So here are some examples of free software renderers. I tried to pick ones that were fairly popular for people who've been using GNU Linux. There we go, perfect. So for people who use GNU Linux, if you're doing anything that's tapping into a graphics card, you're probably familiar with Mesa. The high-performing, if you're doing software rendering, though, they have a renderer called LLVM pipe, which is pretty fast. And then Intel just created one called OpenSWR. There was an article written that tested these on a ManyCore system right here. It's also on Phoronix. But the renderer I'm going to be focusing about as a case study is going to be this one called Vision Array, which was developed originally as an academic project. So Vision Array has the ability to do real-time ray tracing, which allows us to get that speed, but also the high visual fidelity. These benchmarks were extrapolated from a paper that was written about it. The numbers to me are incredible because I had no idea software rendering had come this far. So in this particular case, it's ambient occlusion, and the numbers are millions of rays per second. At the top here, you have the latest and greatest from NVIDIA. You've got a 1080 Ti. It's got roughly 290 million rays per second. But then when you get to the ManyCore chip, this Intel Knights Landing chip, with multiple acceleration algorithms, and what acceleration algorithms do is they make the software rendering much more performant than just using the raw ray tracing algorithm. With these algorithms applied, you get 273 million rays per second, which, if you look at these two, they're pretty close. So the numbers to the left and right, they're accelerated by what are called surface area heuristics, which are kind of arbitrary to the renderer, and bounding volume hierarchies, which is the way we partition the geometry in the scene to determine whether or not a ray hits it and whether we go further along with the ray tracing algorithm. The ones in parentheses are also accelerated additionally by what are called spatial splits. The paper goes into much further detail about that. So what's the feasibility of ManyCore performance? Well, a 1.2 gigahertz system, in this case I'm talking about Knights Landing, a 1.2 gigahertz system with 256 hardware threads and a 64x4 configuration is comparable to the latest generation of NVIDIA GPUs. In this case, the NVIDIA GPUs are using the GPGPU capabilities, so it's all CUDA. It's approximately 94%. So when I see that, when I first started doing this, I was thinking maybe I get close to 30 to even 50%. But the fact that there's software out there that's basically closed the gap, I think that makes a pretty good case for taking what's been driven purely by hardware over the last decade and returning it back to software and obviously making it much more accessible. But is this technology within reach? Yes. We currently have 2 solutions for people who want to get into ManyCore chip development. One of them is OpenPiton, which is spearheaded by the Parallel team at Princeton University. Another one's called Optimus OC, and I believe Stefan Wilentowicz presented on that earlier in the conference. Obviously, that's important. It's driven by FOSSI. And here we actually have an image of the tiles that are laid out for the Piton chip. So about that, OpenPiton. Well, originally it was a Spark v9 Niagara chip taped out in 2015 with 25 cores, 50 threads at 1 gigahertz. Thanks to the framework, the number of cores and threads can scale to be equivalent to Intel Knights Landing and beyond. I believe the limit now is about 500 million cores. Also, my main point of contact with OpenPiton has been Jonathan Balkind, and I believe he presented last year in Bologna. He's very knowledgeable. Also, the other benefit is the instruction set architecture contains vector extensions for SIMD operations. So all of these graphical computations you need to do can be streamlined in a very similar manner to the Intel Knights Landing chip. Added benefit, you've got a Debian GNU Linux port. It's a Spark 64 port ready to go. It's maintained by the community. So if people want to tape out and have the tools there to be productive, they exist. So why not? And then Optimus OC, sponsored and developed by FOSSI members. It's very important. Same principles OpenPiton, except using the OpenRISC instruction set architecture, which also has vector extensions for SIMD operations. One of the things I like about Optimus OC, having gone through the website, it's very intuitive. The process of getting up and running is pretty quick. You can run it on on an emulator or get it running on an FPGA pretty quickly. But wait, didn't you mention something about an online game server? So if people saw the tagline for this on the website, I talk about also a massively multiplayer game server. But thankfully, I didn't have to get too far down that road because benchmarks already exist, albeit using less powerful but highly parallelized hardware. The links to those are going to be on the next slide. The machine that they use for the one I'm going to be talking about here has 32 threads, but already, even with that, you're still getting over 1 million requests per second, and in some cases, multiple millions. And then modern technologies are utilized. So it doesn't have to be C and C++. The technologies utilized are NetI, which is a non-blocking I/O server written in Java, and then also .NET Core, which is the latest and greatest for Microsoft, which is a huge improvement over the previous iterations of it. And then an added benefit is, if we get these ManyCore chips out there, instead of having these giant server farms with racks and racks of multi-core chips, you can consolidate that. So here are the URLs. The ones that have the multi-millions, it comes from these benchmarks here from ASP.NET. I wanted to put this one here as well. The system that's running these benchmarks is, it doesn't have the same bandwidth. It's just a standard multi-core chip, a Xeon series multi-core chip, but the technologies they use there, I think, are just amazing because they're kind of Sinatra-like. For those of you who don't know what Phoenix is a web application framework written in Elixir. The types of Sinatra frameworks they include there are one written in Go that's called Gin. There's Phoenix. There's they also have Node running single-threaded, and then also using Express for cluster mode. One more thing. So I wanted to do one last example of practical use cases for a ManyCore chip, and I think it'll be fairly obvious to the people here. But I just want to make that connection to to how we use computers every day, because I've already spoken about with the software renderer. For people who are doing very graphically intense things, they can appreciate that, and obviously, server admins can appreciate the server uses. But for the everyday person, when do you have parallelization? And so I'll just go ahead and let's put progressive trance. Hopefully that loads quickly. Okay. And then let's get that going. And let's get that going. So as you can see, just using a web browser is a perfect example of this kind of parallelization that I'm talking about. And we're all familiar with this, but I think it's something that we take for granted. And having, actually I'll just stick with audio. There we go. So anytime you're using a web browser, you're tapping into the parallelization of your hardware, and having a ManyCore system that is capable of just from the ground up handling potentially massive amounts of parallelization. Because some people, people I know, have maybe like 10 to 20 tabs open where they're looking at articles, they're watching videos, they're streaming, audio, and just that amalgamation eventually puts a lot of stress, on these smaller core systems. So having, a fabric that can handle that bandwidth of, simultaneous activity, I think would be incredibly useful for everyone. So I'm going to go ahead and actually close this. There we go. So yeah, so practical uses. Web browsers need parallelization in order to stream music and video content simultaneously, and the same goes for web graphics, if you're using Canvas or WebGL. So software rendering could be used to remove these levels of interaction required to communicate with the hardware and potentially increase the drawing speed. So you could have browsers that have, a free libre open source renderer embedded within them, so that there's nothing deferred in that process. And ManyCore chips will make this possible and very efficient. So what is the future? And obviously this is my views on it. I think purpose-built hardware will transition into software abstractions that run on top of a robust network on chip. The idea of a virtual GPU. And to a degree, we're sort of already doing this. And then even with audio, you have OpenAL Soft, which is a software implementation of OpenAL that provides that, that 3D soundscape. More public-facing options. Thanks to these free libre open source hardware frameworks, we can get more chips out there, and with that saturation, hopefully we can get them at a low cost. And then desktop mobile web, I think, will become more accessible and faster due to the embrace of parallelization. And there are companies already trying to push that. Mozilla with Servo is trying to make web much more parallelized than it currently is, so there aren't any bottlenecks in the software. And that's all written in Rust. So I think that there's an opportunity for a perfect marriage between the Rust programming language and ManyCore chips. Thank you.